Hello, and welcome to my talk on the R-code problem is Existential R-complete. In this screencast, I want to show you that ETR-INV is Existential R-complete. Kind of a follow-up screencast to the intro screencast. Again, this is joint work with Mikkel Abrahamsen and Anna Adamaszek, and this is me, Tilman Milzer, or just Til. Okay, so this is a kind of a technical result, but it might be interesting for other reductions. So why might it be interesting for other reductions? In your usual existential R reduction, you usually need to encode addition and multiplication, and that's the most difficult part. So addition just means you have to encode the constraint x plus y equals z, and multiplication you have to encode the constraint x times y equals z. And often the multiplication might be the most difficult to encode. And we can replace this by addition and inversion. So now you don't have to encode multiplication, you only have to encode an inversion in your ETR reduction. And this is what we needed, and it might be useful for other people as well. So let me formally define ETR-INV. ETR-INV, you ask if there exist real variables satisfying constraints of subform addition, inversion, and setting a variable to 1. Furthermore, we require that all the variables are in the range of 1/2 and 2. Okay, and then the theorem is ETR-INV is Existential R-complete. The membership of Existential R is trivial because this is a special case of general for existential theory, existential formulas. Here we have only certain kinds of constraints. In general, we could have all kinds of constraints. Okay, so the proof is otherwise is reduction for the hardness. So first, from a general ETR instance, ETR formula, we simplify so that we have only addition, multiplication, and setting variables to 1. Then we have to scale and shift in order to get the range constraint, and then we have to replace the multiplication by inversion in the last steps. So the first 3 steps are somewhat well known, or they are already appearing in the literature, so we don't really think there's so much new, but replacing by multiplication is new, and nevertheless I will present all 4 parts of the reduction. You can skip to the last part, that's the only thing that's interesting to you. Okay, so the first thing, ETR to ETR, where we only allow addition, multiplication, and setting variables to 1. So let's start with some instance of ETR. Here is some formula, and the first thing we can do a simplification of the Boolean logic. So the Boolean logic, if you think of it, is just not A, where A stands for this bit, and not B, where B stands for that bit. And really here this not we can move inside, so we can replace all other kind of Boolean operators so that we have only not and or, and the not can be pulled in front of each elementary Boolean variable. So once we did this, we can remove the nots. How do we remove the nots? So you have x1 plus x2 equals 1. You just replace it by x1 plus x2 not equal to 1. And similarly, larger can be replaced by smaller equal, and so on. So now we got rid of all the nots. So we needed the nots that were in front of those equations and inequalities. But yeah, so this not equal is not really allowed, so let's get rid of that as well. And a not equal is just either larger or smaller. So we replace not equal by these 2 occurrences. Now we want to get rid of this larger equal. So how we do this? Larger equals either equal or larger. So we got rid of that as well. Now the maybe most interesting part, how do you get rid of larger? It's very simple. If we have some formula larger 0, then that's the same as this formula times z squared equals 1. So if this is larger than 0, surely we find a number, a positive number, such that multiplying with a positive number equals 1. On the other hand, if we know that this holds, since z squared must be positive, we know this must be positive as well. So these two are equivalent, and we got rid of this large root. Now we can get rid of the or. We don't need to. Oh no, we need to get rid of the or. So let's do this. So we can, now we have only equations, and we can make these equations equal to 0 and put everything on the left side. So if we have p equals 0 or q equals 0, then that's equivalent to p times q equals 0. That's very elementary. Because one of those will be satisfied exactly as this is satisfied. Okay, we can also remove the and. This is not necessary, but let's just show you how to do it. If we have a bunch of ands, so now we got rid of the old ors, right? So we have only ands. So this is how the whole formula looks like. And this is equivalent to just squaring each of the polynomials and adding them all up. So if they're all 0, this is going to be 0. If this is 0, then each of these pi squared must be 0, because each term is positive, so larger equal to 0. It cannot be negative. So if one of them is positive, the whole thing is positive, so all must be 0. So now we just get one equation with p equals 0, where p is some arbitrary polynomial. And now the last step remains. We have to substitute all the multiplication and addition. So here, for instance, we have x times x1 times x2, and we can just substitute by y1. Similarly, x3 times x4, we can substitute by y2. So we introduce a new variable and set x1 times x2 to y1 and x3 times x4 to y2. In a similar way that we substitute multiplication, we can substitute addition. y1 plus y2 we can substitute by z1. Adding the extra constraint, so z1 must be y1 plus y2. So in the end, we simplify this polynomial p further and further, adding extra constraint, up to the point that we have a trivial equation, which we just keep there. Okay, so, and then now we found a new formula and in polynomial time, and we have only these three constraints, either addition, multiplication, or setting equal 1. Okay, so now we want to scale. Again, this is kind of standard. So we wanted all our variables can be restricted to this range. So for this we need to know some big hammer. So let's say phi is some formula, ETR formula, then this defines a solution set called semi-algebraic set. Just all the x of Rn which satisfy phi. So this can be an unbounded, really ugly, complicated looking set. But there's a theorem that there exists a larger ball such that if S phi is non-empty, it must intersect this ball. And that's a really powerful theorem. Well, it's kind of clear that such a ball must exist. The question is how large does it need to be. And so there are these bounds of 2 to the L times 8n to the 8n, so double exponential. When is the number of variables phi, and L is the complexity of phi. So here's the typo. Complexity of phi means the number of symbols used to describe phi. That's it. Okay, and what we do is we create a very small number, which is kind of the inverse of that radius here. And how do we create? So this we use to scale everything. So how do we create it? Well, we start with one variable being 1/8, and then we continue squaring. So we have to create this 2 to the minus 2k, and by multiplying two variables, which are already really small, we just add one more. So we have only kind of this polynomial number of equations which we need to add. We need to add a lot of those, and then the last variable will be our really, really small epsilon. And now what we do is we replace each x by an x prime, which is supposed to be really small. And then the addition is substituted by the same addition, because multiplying by x prime doesn't change anything. If we have a multiplication constraint that changes, because here comes on the left side comes 2 epsilons, on the right side just 1. So we have to sneak in another epsilon, and z double prime must be z prime times epsilon. So now here are 2 epsilons and there are also 2 epsilons. And you can see that these two things are equivalent. This kind of, yeah, I will not explain this, but you can figure it out. So and now, before we knew that there must have been a solution in this big ball, if a solution was there at all. And now because we made all these variables much smaller, we know there must be a solution in the small interval -1/8. And that's why we have this +3 here. Yeah, to get really small. Okay, so this is this part, and so this uses powerful Boole theorem, which has been used in other reductions as well. Okay, so the third part of the reduction is just a shift. We somehow want to go from being around 0 to being around 1. We lose here a little bit. And the idea is we replace x by some x prime, which is just shifted. And then if you have some addition constraint, you have to substitute it by a different constraint. And here on the left side we have twice +7/8. But on the right side we have it only once if replaced by z prime. So we have to replace by z double prime, where there must be another +7/8. And you can see that these two are equivalent, and then you have to check that all the variables are within this range bound. And for the multiplication, you have a similar set of constraints that you have to replace by, but they're really large and they're getting really ugly, and that is too much for this talk, but have a look at the paper. Yeah, that's it for this part. And again, this is not surprising, it's kind of standard. But now comes a new thing. We want to show that ETR-INV is hard, so we have to replace multiplication. So this becomes really horribly technical, and most of it is not very interesting. So let's ignore the range constraints, okay? So let's ignore this part. We just want to replace multiplication by inversion, and we don't care for the range. So the first step is we want to do this is we have to build x squared. How do we build x squared? Well, by this formula here. So this term, to generate it, we only use inversion and addition again, and inversion again. They're kind of, to create this term, you have a lot of hidden variables, but you see all the time only addition and inversion is needed, and you can see that this term is equivalent to x squared. So if you have x, you can build x squared using some sequence of inequalities. We just use addition and multiplication. Okay, so we can build squaring. Now we have to build multiplication. That's pretty easy. So we can build x plus y squared, and we subtract this x squared and y squared, and divide by 2, and what remains is x times y. So in this way, once we can build squaring, we can build multiplication easily. This becomes more difficult if you want all the variables to keep in the range. It's kind of a long list of constraints that you have to add. But yeah, it's new. It works. And yeah, it's kind of surprising that this was not known before, but now we know. And thank you for attention. And again, this was joint work with Mikkel Abrahamsen and Anna